Welcome to Oddly Real. I'm Nem Stefanovic. Information actually has physical effects on our universe. We're familiar with physical laws that govern things like the forces of nature and how they interact with matter and energy. These laws determine how the universe works, including actions and reactions, how chemical processes take place, and the effects that we experience in our everyday lives. But did you know that there are also laws of information that govern the behavior of the universe? I don't mean in some abstract sense. I mean there are rules for how our universe treats information, in that they have very real physical consequences in our reality. For example, if you write down on a piece of paper some information, then erase it using an eraser, you will necessarily produce a change elsewhere in the universe as a result of removing that information from the paper. In this episode, we'll discuss information as it applies to processes in our universe and the consequences for changes to that information. What exactly do we mean by information? We know that books hold information. We can store files on computers that store information. We can watch videos and listen to music, which can convey information. Notice that the actual physical medium of information transmission doesn't matter. Clearly, we have some kind of intuition for information. For example, let's say I give you a note with a message. Then I have given you added information. However, if the note is smudged or not clear, then you lack that information. Also, we can say that if I gave you a longer note, you'd expect there to be more information compared to a shorter note. In general, we say that information in a message is the ability to distinguish between alternative possible messages. So what does that mean? Well, let's say we are sending a message by writing words in a book. We can write a book using an enormously large number of different combinations of words. There are a lot of alternative possibilities for how to write that book. So that means that a book can convey a tremendous amount of information in its content. Let's say that you can write something down a total of m different ways. You can figure out how many bits you need to represent those different possibilities m, which we call h, by using the formula that h is equal to the log of base 2 of m. Those number of bits have a meaning. One way to think about it is that it is a measure of information content of a message. Alternatively, it can also be thought of as a measure of the lack of information that we have before we've received the message. So how does this all tie back to how information can affect our physical universe? Well, it turns out that information has a very deep relationship with a property from thermodynamics called entropy. Entropy is a measure of possibilities. It's the number of possibilities that the atomic arrangements called microstates of a system can be arranged so that the system looks like it does and has the properties that we measure, which we call the macrostate. You can arrange atoms lots and lots of different ways in a system without changing what we see at the macro level. If there are more ways to arrange the atoms, we say that there's more entropy. Next, we will look at two fundamental laws from thermodynamics about the way our universe works. The first law states that energy can neither be created nor destroyed. It is always conserved. For example, we can touch two objects together that have different temperatures and different energies. When the objects touch, energy is transferred from the hot object to the cold object until both are at the same temperature. If you calculate the energy of the system in the end, it will exactly match the energy that it had before contact was made by the objects. However, this law is not sufficient on its own, since it doesn't prohibit a transfer of energy in the reverse direction. For example, you can take two objects of equal temperature that are in contact, and you could imagine that one of the objects could heat up to a higher temperature while the other loses heat to become colder. Yet this doesn't happen in reality. We only see energy flow from hot objects to cold ones, not the other way around. Clearly, we're missing something. That would be the second law of thermodynamics, which depends on the notion of entropy. The second law states that the total entropy of a system can never decrease. In the example of the hot and cold objects, when the hot and cold objects are separated, they have lower entropy than when they are connected. Why? Well, the colder object will increase in temperature, giving its atoms more motion and more possibilities to rearrange themselves and increase entropy. The hotter object will lose that energy, but it will not lose as much entropy as the colder object has gained. The entropy of the system overall is larger. Hence, the second law of thermodynamics ensures that heat flows from a hot object to a cold one and not the other way around. But here's the interesting part. It turns out that entropy is actually information. We can measure properties of the macro state like temperature, pressure, mass, and others. However, we don't know the details of the microstates. We just know the number of possibilities. So, for example, there could be m different microstates for a system in total, and we don't know which microstate the system is in. However, we can encode the possibilities of the microstates, all the possible arrangements of the atoms, as a measure of missing bits of information using the formula log base 2m. In fact, we call log base 2m equal to h, the information entropy. Then thermodynamic entropy is K2 times h. So thermodynamic entropy is the same as information entropy. The value K2 ends up representing the thermodynamic entropy of one missing bit of microstate information, which is 10 to the power of minus 23 joules per Kelvin per bit. So imagine a situation in which you have two containers with two different gases in them. If we were to connect the boxes and allow the gas to pass through the containers, the gases would mix up and the entropy would increase. This happens because there are more possibilities now for how the gas molecules can move around and rearrange themselves. But think about this from the information perspective. When the gases are separate, we know one extra bit of information. We know one gas is all on one side and the other gas is all on the other side. So we know for each molecule where it is between the two possible locations. So if we mix the gases together, then any of the molecules, let's say there's n of them, can be in either of the boxes. We are lacking more information about the microstates. We've lost that one bit of information for the molecules. That means there's a K2 times n increase in entropy. The total thermodynamic entropy is K2 times the information that we lack about the microstate. In reality, microstates are always changing with time, since the atoms and molecules are in motion and rearranging themselves over time. They can move around so much that they can actually move into a different macrostate. So their measured properties have changed. However, there's a law called the principle of microstate information that must be followed. Specifically, as the microstates change, microstate information must be preserved. The microstates cannot evolve so that they end up in a situation where there is less information in how they are arranged. That would also violate the second law of thermodynamics, since it would also mean that entropy would have gone down. Thus, we can guarantee that two different microstates must end up as two distinct different microstates, and not the same one. Another way to think about this is that the universe does not discard information. This has big implications for the workings of the universe. There is no process in the universe that can erase information for free without some kind of a price to be paid. So quite literally, if you erase a note on paper or you delete a file on your computer, you will invariably introduce a change into the universe to compensate for that action of deletion. Here's a simple example. Let's say you slid an object across a table and the object eventually came to a stop due to friction. At this point, the object's past has been erased. There's no way to tell if the object slid from one end of the table or another, or perhaps it moved along some other trajectory. Whatever happened is now gone. But you'll also notice that the object is a little bit warmer from the heat generated by the friction that stopped it. In this case, the entropy of the object has gone up. Let's look at a more surprising situation involving computers. When a computer is running and executing computations, it's also generating waste heat. Modern computers have immense numbers of transistors or switches concentrated in a very small space on the processor that are operating at very high speeds. It's not surprising to imagine that the electrical paths will be in frequent use, moving electrons and generating heat due to electrical path resistance. However, what might be surprising is that even if you could optimize these processes and reduce or eliminate these heat sources, the computer would still generate lost heat. But why? It's actually due to lost information. If you take a basic computational task, like adding two numbers like 5 and 10, you'd get 15. However, if you try to figure out what values were added to get 15, you wouldn't know. It could have been 9 and 6 or 11 and 4. This process is not logically reversible. Information has been lost, and necessarily there must be an increase in entropy as lost heat. The simplest possible erasure of information happens at the bit level. The loss of a single bit of information results in an increase in entropy of at least K2, or 10 to the power of minus 23 joules per Kelvin per bit. These erasures happen in many parts of a computer, but consider a basic OR logic gate. Its output will be 1 if any or both of its inputs are 1. So there are 3 situations where it can produce a 1 output, and we couldn't tell which it is by knowing just the output value. It's not reversible, and information is lost, and entropy goes up. Interestingly, it turns out that it can be proved that all computer operations can, in theory, be made to be reversible so that no information is lost. The only exception is erasure. It is possible to construct logic gates that are reversible and will not suffer from information loss and hence heat loss. This can happen by making sure that you can determine the inputs going backwards from the output information. You'd need to ensure that the outputs of a gate match the number of inputs to prevent information loss. Yet there is also a cost to doing this too. You don't waste heat anymore, but now you're wasting information, since you have extra outputs that you don't need. And again, if you want to get rid of that information, you'll have to pay the price of added entropy when you erase it. So I hope you think twice now before you erase information. I hope you enjoyed this episode, and remember, oddly real, really interesting.